get straight into it. Welcome everyone. I see a few new names tonight. So for those who haven't been on with us until now, my name is Catherine. I'm the Business Development Officer at Partners in Ag, and I would like to welcome you all here tonight. I'd also like to acknowledge the traditional owners on the land on which we all meet and pay respects to their elders, past, present, and emerging. Tonight, this webinar series has been supported by the Wimmera Catchment Management Authority with funding from the National Land Care Program. So thank you very much to both of those organisations for supporting us with this webinar series. We do have quite a number of people joining us tonight. So in terms of questions for David, please put them in the chat function. Between David and myself, we'll be monitoring that during the evening, and there will be a chance at the end to ask questions. David, we might just get straight into it before my internet drops out again, and I'll hand over to you.
Thanks, Catherine. No worries. Yep, it's always good to not take that risk. G'day, everyone. I'm just going to share my screen and get the right screen going. Can you guys see that? Hopefully everyone can see that. If someone can give me something in the chat just to make sure it's all working. Yep, thanks, Catherine. So yeah, welcome back everyone. Those of you that are new, the other ones, parts 1 and 2 or sessions 1 and 2 have been put onto YouTube, so feel free to do them first. Because yeah, it is a bit of a sequence to this, but welcome back to the Reboot My Soil Health webinar series, where we're just kind of learning how to, or the process to follow to kind of assess a soil's health, work out whether it's got weak links or what we call soil constraints, and then kind of identify some possible management options to fixing any soil constraints. And we're using a bit of what I call a modern 21st century approach to soils, and we're looking at soils as a complex system with plant roots as a really big influencing driver of soil functions. So you kind of, your topsoil without plants growing in it is not really a topsoil, I'm sorry to say, because your plants and their roots in particular are a really important part of a topsoil system. So you've got your plants and their roots, you've got all the soil life and biology, and then you've got the minerals and the chemistry, and then you've got air and water. And all of those things combine into a topsoil like we have in front of us. This one's near Beechworth, which had some pretty serious soil constraints like compaction and high exchangeable aluminium, which we're going to touch on tonight. And yeah, the guys were able to use cover crops and some liming and a few other things to improve that soil so it can grow them vegetables. So that's what we're on. We're on this challenge of rebooting our soil. So I do apologise, everyone. I am in a motel again. I will be home next week, but it's been a long month on the road. And so I've got a single screen, so I don't have all the bells and whistles on my computer tonight. But we're on this journey that P.A. Yeomans, who was a really famous regen ag rock star from the 1940s, so he's like the Neil Young of regen ag, and he said that agriculture itself can be a soil making process. So we can kind of build and maintain our soil asset or the soil health of our soil, while also doing agriculture, which is kind of important because you want to make money while you're doing all this stuff as well. And here's Michael Baldry and a few guys at Harden in New South Wales that are on this same challenge in grazing and mixed farming country. All right, so let's keep rolling. And we've explored in session 1, we touched on briefly soil types, understanding soil types and how that's important when you're making management decisions around the type of enterprise you're growing, your yield or productivity goals. If you're doing fertilizers and agronomy, you know, why am I expecting this much yield on that soil type? We should be adjusting my fertilizers and soil amendments to match the soil type. That's a really important skill. And then the second skill that obviously this course is really, the second skill about soil type is deciding then to match your enterprise and your production goals to the soil type. But the third really important soil management skill is managing soil health, which is really what this webinar series is about. And, you know, I put in there a question because we touched on carbon last week, but it was all about You know, okay, we've measured the soil carbon. We know carbon's important for my soil. It helps with structure. It feeds all the life in the soil. They're carbohydrates, and they need carbohydrates. They're not just into protein only. They need carbs, and we need it for nutrient cycling, for water holding capacity, a whole lot of stuff. So what is a good level to aim for? And so we had a look at some carbon levels, and if you have a soil test, hopefully you were working along with that soil test. And then we've got to decide on a benchmark. What's a good level? What's relevant for my soil type, in my climate, in my region? So some soil health properties like carbon can be a little bit, they're not black and white numbers, because it depends a little bit on soil texture and rainfall and things. But there's a minimum amount of soil carbon I need to get structure, to have soil function, to hold my nitrogen, because nitrogen is held in soil organic matter. That's the main place. So if you're chucking out fertilizers, nitrogen fertilizers, and you don't have organic matter, you're not going to hold any of that nitrogen. Sorry to tell you that. So we need a good level of organic matter and carbon. And we had a look at both of those two things last time. And there was a question in there from Jen that we didn't hit last time, and that was, we didn't cover, and that was about, you know, is the level of carbon or carbon to nitrogen ratio going to be adjusted for soil type and grazing versus cropping or things like that? And the answer is some of the soil health properties are context specific. So yes, they are variable, but some of them are quite black and white and universal, if that makes sense, Jen. So for example, the carbon to nitrogen ratio, which I gave you guys a bit of a benchmark of between 10 to 1 to 21, that is kind of a fairly universal parameter for soil function for living systems. Whereas the total carbon, it will vary a little bit, organic carbon levels, depending on if it's a sandy soil, the benchmark will probably be a bit lower than a clay soil. But there is a minimum to aim for, because whatever you're doing, veggies, cropping or grazing, you need soil structure. So, you know, you need at least some carbon there, but it is a little bit context specific. And you'll know whether you're reaching your carbon levels, not just because the soil test has a good number on it, or there's a colourful chart telling you it's green, it's in the good, but because you'll start to see that structure, and agronomically in the field, you'll see better water holding capacity, better infiltration of water through better structure. Crops will hang on longer in dry periods. All of those symptoms or signs that you've got better soil function. So this is the other message that I've been trying to get across in this course is, don't just go on your soil test alone. Use soil test in combination with your field, what you're observing in the field, not just the crops and pastures, but the soil functioning. Okay, so with that in mind, everyone, there's a bit of resources here and there that we've already mentioned, and hopefully you've got a soil action plan copy that Catherine sent around, which looks like this, and you can just be filling in your results on it, along with finding a benchmark and things like that as we go, if you want to, if you've got a soil test and that's what you want to do. I'll just check that chat in there. That's all good, Charlotte. Yep, yeah, you can watch it on YouTube. Just Charlotte, just putting that she missed last week. All good. You can put me on the big screen while you're cooking in the kitchen, and I can be on the 60-inch screen telling you about soil carbon. You probably go crazy if you do that, so don't do that. Okay, and of course we're looking at soil health, and of course that's what the course is about, but we're mainly focusing on using a soil test to assess soil health and identify soil constraints, not nutrient constraints. That's a separate issue. Soil constraints like compaction, aluminium, pH, but it is important to get out and field assess the soil as well, and it's hard to teach that, and certainly we're not covering it in this specific course as much. So remembering those 3 core skills of field assessment of soil, using soil tests and benchmarking, that's what we've been practicing, core skills 2 and 3, and we're practicing the third of the management skills, which is managing soil health. Sorry, there's a spelling mistake there. All right, so today we're going to jump into probably the most tricky part of soil theory. It often trips people up, and it's not because it's too difficult. It's just because it's a little bit abstract, the whole idea of cations and exchangeable stuff. It's an abstract concept in a way because we can't see it. So we're going to be talking about exchangeable cations, like exchangeable magnesium and aluminium, and the soil colloids. So it can be a tricky part of soil theory, and sometimes people really get challenged by it, and that's fair enough. I was certainly when I was learning about soils. So hopefully I can keep it in plain English as much as possible, and we'll see how we go anyway. But you can watch it again, and there's other YouTube videos on this whole topic that's probably worth exploring too later. If you've got any comments, please put them into chat. Don't put your hand up, just put them into chat. All right, let's just do a quick refresher that we're managing soil health. We're using a soil test to help us assess a soil's condition so we can identify soil constraints. And a soil constraint is pretty much anything that's limiting plant roots from expressing their full genetic potential. So anything that inhibits a plant from expressing its full genetic potential of its root system is a soil constraint. And because the root system of plants is what really drives the functioning of soils, because they're bringing in carbohydrates and organic matter through photosynthesis, and that feeds the whole soil community. It modifies the soil chemistry, and the plant kind of then helps with the soil life, and the minerals helps create that functioning topsoil. And we're going through a checklist to check our soil health, and the checklist is not too long, but it's just like a checklist of a vehicle. When you're buying a second-hand vehicle, you kind of got a checklist in your mind: body condition, gearbox, black smoke, is there an engine in the front, what are the tires like. You're just going to go through a checklist, and it's the same with soils. It's not too complicated. And we've been working through a checklist, and we've covered carbon and carbon nitrogen ratio, and tonight we're covering the cation balances and pH. Next week we'll do soil salinity. And the checklist also includes field assessment, which we don't cover in the course as much, and that's ground cover, soil structure, root activity, soil biology, things like that, which are also really important, but a normal agronomic test can't really help you with most of that stuff. They're a little bit limiting. They aren't perfect soil agronomic tests. They're kind of a useful tool, but in the 21st century, they are a little bit limiting because they're kind of not capturing everything. Okay, so let's jump into the next thing on our soil health checklist that we've just been working on the last couple of weeks, and that is soil pH. So we looked at carbon, we've looked at carbon nitrogen ratio, or the quality of my organic matter. Now let's look at pH, which is a really important aspect of your soil. It influences a lot of things in your soil, functions in your soil, like nutrient cycling, but also soil biology. So pH is a really important aspect or parameter of your soil system. But having said that, it's really important to remember that the life in the soil and the organic matter and the plants also influence pH. So it's a two-way relationship. It's not just the pH influences plants and things. Plants and life in soil influences the pH. So it's a two-way relationship, and that's quite different than 20th century agronomy, where it's like, oh no, my pH is out, I have to add lime because until I fix the pH, plants aren't going to grow, which sometimes definitely applies, but you've just always got to remember that the living part of the soil also does modify pH, and that's the other dimension that's going on. So pH is measuring the acidity or alkalinity of your soil. It's pretty straightforward. We're all pretty comfortable with that probably. What it actually measures is the hydrogen ions, what we call active or exchangeable hydrogen, which are kind of living in one part of your soil, what we call the colloid zone, I call it. One of the active parts of your soil, you have these hydrogen ions hanging around, and the more hydrogen ions you have, the more acidity you have. So the more acid, the lower the pH, but the more hydrogen. And it's important because it does influence soil function. So sometimes it's not as important as other aspects of soil health, but it can be, in a lot of situations, really important. There's two ways that it's measured. So if you remember, we were looking at pulling apart soil tests last week and how to pull them apart and read them. There's two types of methods used to measure pH in your soil, and one is the 1 to 5 water method, and the other one is the calcium chloride method. And you can see me here doing a pH demonstration for some graziers in New South Wales. And I'm using a field kit for pH, which is kind of similar to the 1 to 5 water method. So that's on the soil test. You're going to get either of those methods. So if I have a look at a soil test, I'll just pull one up. Let's get one out of the Victorian cropping paddock. So here's one here, and you can see at the top of this test, I'll just get my annotation going. At the top of this test here, I've got, remember that we're looking for the indicators that we're relevant, we want to look at, and they've put pH right at the top. And in fact, they've done pH in the two different methods. So you can sort of see this particular lab puts the method of the pH in brackets. So they used 1 to 5 water, H2O, and they got 4.9 in the pH. When they did the calcium chloride method, which is this separate, different way of measuring pH, you can see the result is 4.3. So people use either method. The really important thing is that when you're benchmarking or assessing against some reference, make sure it was in the same method. So if your neighbour says, oh, my pH is 6, and you say, oh, my pH is 5, make sure you talk in the same calcium chloride or water method, otherwise you're not talking about the same thing, and that's important. So you can sort of see the next stage in using a soil test. You've got your indicator, in this case the aspect of soil is pH that we want to look at, measure, and then we've got our result, which is good because we pay the money to give us some results. And then you can see that this Insight Tech test lays it out, the benchmarking in this particular way. We've got low to excess, and then they give you this what they call sufficiency range, which is kind of like the benchmark. So this is a good target according to them. Now you've got to trust their benchmarks, and we had a chat about that last week, that don't always trust benchmarks on soil tests. You've got to check that they've been regionally adapted to your soil type, your climate and your crop. So that's really important, and labs don't always do that. So you can kind of see in this particular case the pH is low and it's in the red. That means you're going to be spending money with me or whoever. It means it's out of balance, and the technical definition, if we accept the benchmarking results, is that we have a soil constraint. That pH is probably interfering with soil function and a nice smoothly flowing soil system, which will optimize conditions for plant roots to grow, and that's what we're trying to achieve. So that would be the general consensus based on that. And remembering the key thing about soil constraints is it's not just potentially costing you money in lost yield, it's going to cost you money to fix the problem. So soil constraints, soil health issues in the farm business have a double whammy to the profit equation. They reduce your potential yield, and that's a loss of potential income, whether it's pH or structure or water holding ability, that's potential yield loss. And the second thing is it's going to cost you money and effort to fix it. So unless we can fix it while making money, we can, but it's still going to cost you a little bit in some way, shape or form to repair the problem. So in this case, obviously people often use lime to kind of fix their pH, but we can come back to that later. So that's an example for you. We've got the two different methods. The scale is 0 to 14, so 7 is neutral, above is alkaline, below is acid. And so if you have a soil test, please hunt down your soil pH. I'm going to just have a look at one or two more. We've just had a look at that Victorian cropping paddock. Let's have a look at a horticulture paddock here now, growing veggies. And you can see this is this lab called, sorry everyone, I'll just get it up. It's the Vita Lab in Tasmania. It's used, they're a very big lab that services the horticulture industry. And you can see their lab, the test is called Express Soil or whatever. But you can see they've also put pH near the top because they consider it to be important. Here's our column of all the things they've analysed for us, and they've done the pH in both methods as well. And that's because either method is quite widely used, so you might have someone that prefers to read the water or the calcium chloride. So they're just different methods, and you can see that the calcium chloride is always a bit lower because it's a stronger extractant, so it measures more of the hydrogen in the soil, so you'll get a more detailed reading, I guess is one way to put it. And you can see they've given a range. So you can see there for water, it's between 6 and 7. For cal chloride, they want you to be over 5.3. So they're saying, in this case, they're saying this soil is slightly acidic. And it's not super acidic compared to the other one, which was like 4.3 or something. This one's 5.18, but they're saying for veggie growing or this particular crop, you should be over that 5.3. So it's kind of marginal. It's not super low. You know, you might say, well, do I need to invest in fixing that now? Is it not a priority issue for me? You'd want to check some other aspects of the paddock. So you might check the plants, check the other nutrients, any other soil constraints, and a few other things that we'll go through. But you can sort of see it's kind of marginal. It's not really acidic like that previous paddock. And I'll get one more up just so we can look at a different lab. This is a grazing paddock in North Queensland, just to give you guys a mix-up. This is a different lab too. This is EAL, who give you plenty of detail on their tests. So that's the lab based at Lismore in Northern New South Wales at Southern Cross Uni. And you can sort of see there that they've got the pH in water, the water method. Notice how they put their method in its own column. So it's clear, oh yeah, they've measured in water. There's the pH, and we could ask them to do calcium chloride if we wanted to. It's just this particular test we didn't ask them. And there's our result there, 6.03 in water. So that will be a bit lower in calcium chloride, because if we measured it in that other method, it's always going to be lower because it's a stronger extractant. And you can see there they've given some benchmarks as well. And that, again, these are the 5 elements of a soil test. Is the, sorry everyone, I'm just trying to get this working. The 5 elements of the soil test is the indicator, the unit of measurement, the method, etc., and then some benchmarks. So obviously these are the different elements of a soil test, and different soil tests lay things out differently. Today we were looking at soil tests all day as well with a different lab, CESL or SESL, and they put it in a different format again. Okay, so hopefully that's making sense to everyone, and if you have got your soil test and you've read your pH and it's really, really low, then ring me up later and I'll sell you some lime. No, I'm just kidding. But yeah, now you have to make a decision as to, do I lime, or are there some other things I can do to minimize this acidity or to counteract it? And obviously this final key part of reading the soil test and assessing soil health is benchmarking. So we just did that on a couple of the soils. And if we go back to our Western Victoria soil, cropping soil, we can see that we have this quite low level. If I just stick on calcium chloride, it's low, and they're saying you need to be over 4.7, you know, within that range there to be for crops, for mixed crops in that area. So we're definitely most likely got a soil constraint here. And so you're making a note about that. You're going, righto, this is a potential soil constraint which is costing me yield. And the soil biological system is probably being impacted, as well as the nutrient cycling system in the soil, which is kind of related to the biological system because they're at the heart of nutrient cycling for most nutrient cycles. So yeah, you can sort of see that it can open a can of worms, excuse the pun, for some problems in my soil. Okay, I'm going to keep going, everyone. So the question of where to get your target benchmarks from is really important, as we've discussed. And I'm just giving you some very broad general targets, mindful that some specialty crops can be outside this range, and it's good to get that regionally appropriate benchmarks if you're not sure whether the benchmarks on the soil test have been regionally adapted. But yeah, there's some general targets, you know, in calcium chloride pH of trying to hit 6 or 5.5 to 6, and getting grazing over about 5.5. There are lots of grasses, pasture grasses, are quite tolerant of lower acidity, so lower pH. So a lot of grasses can be quite tolerant of acid conditions, but the thing is the legumes and the other, you know, broadleaves, if you're growing chicory or plantain or these other guys, they're not as tolerant. So just because your grasses don't mind it, if the other things are important, and the soil biological conditions will be optimum at that more neutral, towards neutral pH as well. So it's probably really worth, you know, thinking about those aspects of your soil, not just your main plant or whatever. So it's taking a more holistic view. Okay, so I hope that makes sense to everyone. If there's any questions around pH, feel free to throw them in. Obviously, if you're well within your target, then that's good. You've got to think about how you can maintain that soil equilibrium and not drive it to be too acid. If you're outside your target range, then that's marginal. You know, do I need to invest in fixing the problem, or is it really a problem? Let me check field conditions. For example, in pastures, you can have slight marginal acidity or low pH, and the legumes are still going really well, and they're quite sensitive. So if they're still growing well, do I really need to worry? But there is a threshold, and once you sort of drop below a threshold, which is often around 5 or just under 5 in calcium chloride, you can really throw the system out. So it's better not to go that low. Remembering that pH, I'll get up the whiteboard just so I can practice the whiteboard and feel groovy and modern. Hang on a minute, everyone. Where's our whiteboard? Don't even know where it is. No, don't do that, Dave. Whiteboard's gone walkabout on me. Never mind, I can't use it. I'm not that groovy and I'm not that modern. All right, forget that. Okay, everyone, I'll just get the annotation going. Sorry, last time I worked out how to use the whiteboard. Now I don't know how to use it. All right, so if I just get the squiggly doodah going, just remembering with your pH that when you go from a 7 pH down to a 6 pH, that's not just 1 time more acidity, it's 10 times, because pH is a log measurement. So when I go from 7 to 6, that's 10 times more acid. When I go from 6 to 5, that's another 10 times more acid. So altogether, that's 100 times more acid in my soil when I go from 7 to 5. So can everyone see that when you go under 5, there's heaps more acidity than when you're around 6, 6.5. So it's better not to get to that position. So that's where monitoring your pH regularly and using a little bit of lime, or using compost humus management, or just not encouraging acidity with good fertilizer practices and soil organic matter and roots, and just getting biological and buffering stability with humus. That's really important. So just doing those things rather than letting the soil collapse and then having to add all this lime and shock the system and all that sort of thing. As usual, it's all about stitch in time saves 9. Okay, so I hope that makes sense. And the way people often, sorry, I don't know what's happening here. My computer's mucking around a bit. The way people deal with their liming, obviously, is adding lime. Sorry, their pH is often they add lime. But as I mentioned, if you keep good organic matter and you don't overuse nitrogen fertilizers or have too many clovers all the time in the pasture, if it's pasture, then you're going to minimize the acid process. But in a lot of Australian areas, acidification is a natural process. But believe it or not, I guess the modern view of soils is if I can keep soils in a really good equilibrium, especially the organic matter biological equilibrium, it can actually counter or minimize that acidification process. And you do see that where people change their grazing, improve the organic matter, and the pH stabilizes in an area that traditionally you would go acid and you would lime quite regularly. So these things do happen. But yeah, it's about taking a holistic approach. Okay, so have a think about, if you have a low pH, what you can do to improve your place on your pH on your place. And as I've shown you in this picture, which is some lime going out on a paddock near home at Albury, don't lime because the neighbour limes. Don't lime because the accountant said it's tax time and you've got to spend money. Don't lime because the lime company says you need lime. Lime because you've measured your pH, you have a target, and you want to keep your soil within that target so the soil operates really well. That's why you lime. Don't lime because the neighbour does it, or because everyone else used to do it or does it, or because the accountant wants to spend money, your money. Just do it for an agronomic target. That's, I guess, the thing. There's a questions come in there. Charlotte's got in there. Increased organic matter decreases pH. Yeah, okay, Charlotte. So yes, it is a traditional thinking that if I increase organic matter, if I add mulches and things, that I will acidify the soil. It doesn't necessarily happen like that. So I'm going to actually show you an example, Charlotte. So yes, the conventional wisdom is that I can acidify my soil by adding quite a lot of organic matter, particularly. Not so much manures, it's more actually, manuring sometimes has an alkalizing effect. It depends on the manure. but certainly, you know, mulches and some compost and stuff is deemed to increase acidity. And I'd suggest to you that that's not always the case. It depends a bit on the quality of the material and the soil type and climate that it's going into, and the other management practices. Yeah, so just to finish that off, Charlotte, I'll show you an example from 9 soils, and those of you that have been on the previous webinars will know that I've got these 9 soils that we've been looking at, and we were looking at their total fertility. But here's the 9 soils and their key soil health properties of those 9 soils, and here's pH at the top, so hopefully everyone can see that. We're on the pH, which is the top row there. And this soil here, which I showed you a picture of, it's that vanilla soil with 16% carbon, which was created through heavy mulching of the vanilla beds. So hopefully you remember that soil. If you haven't seen that and you're watching this video, go back and watch the previous videos, because it's a pretty remarkable soil. But Charlotte, despite 10 to 12 years of very heavy mulching, like really heavy mulching, and you can see the YouTube video on that farm to get a feel for how heavy the mulch is, the pH is stabilised at 6.6. Now that area is a 4 or 5 metre rainfall zone in the tropics, and that gets acid. Those soils up there can get acidity big time. So it's not like it's a very kind environment. It's a naturally highly acid risk environment, but only with mulch, no liming, that soil has come into an equilibrium. So it's quite a unique situation. It's also, you can see the carbon level there, 16%, which I think we looked at last week. And the humus, the kind of humus is a colloid and it has a buffer. This is how it's working. It has a chemical buffering process. It has helped to stabilise that because the humus has gone through the roof in this soil as well. So that's kind of an example for you, Charlotte. But there are times where soils will acidify, and you'll often hear people go under pine needles, under a tree. It'll be really acid. But we did a job not far out of Ballarat a couple of weeks ago, a workshop, Coglan's Creek, I think it was, and the pH in the humus layer was actually quite close to neutral. So yeah, it does depend. The raw needles could be acid, but the humus layer can be more neutral. So you really actually just got to check. So I wouldn't assume that. Sorry, everyone, I kind of went on a bit there, but hopefully that makes sense, Charlotte. And Liz, yeah, so there's a few factors. So rainfall and natural weathering drive acidity, low organic matter drives acidity, high use of nitrogen fertilizers and or heaps of legumes all the time that can generate excess nitrates as they break down. Those things are all driving acidity. Losing my humus, so I no longer have buffering capacity. Some soil mineral types are more prone to acidity. So you've got a combination of factors, and I guess you're trying to kind of go against them. The more rainfall, generally the more risk of acidity too. That's just that driving factor of weathering. So hopefully that makes sense, Liz. Yeah, so you can fix your pH with lime, but if I haven't got organic matter and biological function, it's going to go back to acidity quite quickly, a year, 3 years, 5 years, depends where you are. So you'll be liming the paddock again. And that it may be something you do have to do on an ongoing basis, but if you improve the biological and humus dimension to your soil, then you can get away with less lime, if that makes sense. All right, everyone, I'll keep rolling. So hopefully I'm not going too fast or too slow. I have had 2 days of doing reading soil tests face to face. So if I start to zone out, please forgive me. Okay, so we'll keep going, and we just talked about that. So yeah, you guys have just thrown some burning questions. So hopefully that gives you a bit of feel for pH. So I'll just see if I've missed one last chat. No worries, thanks, Liz. Okay, so let's jump into the big kahuna. So if you have been drinking alcohol, then there's no way you're going to have any hope of following me in this next session. And I did warn you last week not to drink any alcohol or to have no alcohol beer or beer with no alcohol in it. I think they sell that now. I don't drink, and I wouldn't drink that stuff either. But yeah, that's probably the only alcohol or beer you're allowed to drink. Although it is footy night, unfortunately, we're not watching State of Origin, but we'll watch it later. Okay, so now we're getting on to the difficult part of soils, the soil health side, and that's something called the cations and the exchangeable cation balances, sometimes called base saturation. So this is one of the key important areas of your soil's health. So organic matter and the carbon nitrogen ratio we explored last week is a really important aspect of your soil. And another really important aspect of your soil is the cations. So There's also things like the physical structure, salinity, which we'll cover next week, biological dimensions to the soil. All of them are really important, but a normal test can't measure them. So the last sort of main thing that a normal test can help you with is this exchangeable cation balances. So let's jump into it. Hold on to your hats because we're doing it at 8 o'clock at night, and let's rip into it. So the key thing, if I can get this to work again, the key thing about your soil is not only does it have organic matter and life in it and roots and pore spaces and all that sort of stuff, it contains something called colloids. Now, colloids are, sometimes people see them as a bit mysterious, but they're not really. So here's an example of a colloid for you. It's milk. So the question is, what is the main ingredient that you buy when you buy milk? What is actually the main ingredient you buy? If anyone wants to punch something into chat, feel free, but I'm just going to, because of time, I'm going to keep going. But the main ingredient you buy when you buy milk is water. Okay, so if you thought it was calcium, then you've just been conned by the marketing ads. The main ingredient is water. So the question is, why is the water white? And why is the milk white? Why is the water now white colour? And the reason is, it's not because the cow makes it white. Well, it is, but that doesn't give us an answer. And it's not because it's vanilla milk, right? So those are not the right answers. The right answer is it's because the water contains fat. So this water is containing fat, and the fat is actually floating, if you like, or what we call in suspension in the water. So when you're holding a cup of milk, even vegan milk, and it's white or creamy color, it's because there's particles in it that are staying in suspension. So in milk, it's fat. The fat is staying, even low-fat milk or A2 milk or whatever, A1 milk, A12 milk, the fat is staying in suspension. So the fat doesn't dissolve, it doesn't disappear. Like if I chuck table salt or urea into water, it will dissolve and disappear, get disassociated in the water. What's happening though is that the little fat particles are staying in suspension. Everyone see that picture there of the little fat particles, which are green because this is green milk. It's for the Canberrators or something. And then over here you've got, Port Adelaide if you're into AFL. And then over here you've got this, what we've done is we've put lemon juice into the milk or vinegar, and we've broken the colloid behavior. So everyone knows what happens when you put lemon juice in milk. You'll curdle it and you'll get the solids and the liquids separate. So that what's happened is you've disrupted the colloid. Now the thing about fat in water, or these things, what they are is they're colloids. And a colloid is a really, really small particle. And when something is, and it has it, and the other special thing about a colloid is not just it's small, like talcum powder fine, or clay, but the second thing about it is it has a charge. It has an electrostatic charge on the surface. So think about each fat molecule in this milk here has a charge on the surface. And as the fat particles are swirling around in the water, they're bouncing off each other and they're staying in suspension because so that's what a colloid does. It has a charge, it's small and it has a charge, and therefore it has this particular behavior. Another example of a colloid that we use every day is aerosols in the toilet. When you go to the dunny and you spray the aerosol, the gas contains colloid scent molecule particles. So the particles, if you like, are held in a gas rather than a liquid, just a different type of colloid. Okay, so they have this charge on the surface, and colloids, that's what makes colloids a bit special. And your soil contains colloids, and the reason it contains colloids is that what have I done here? Is that soils contain clay, and clay is a colloid. So clays are colloids, means clays are really, really tiny. We all know that. It's really smooth to touch because the particles are really small. And clays have a charge on their surfaces, and that makes them a colloid, and they behave like colloids. Not like colloids in water as such. Well, they do sometimes, but they're colloids. So where did the soil's colloid come from? It's basically because your rocks break down to minerals. Remember this soil here on the Liverpool Range in central New South Wales, the rocks are still breaking down to minerals, and that's why the topsoil is still full of rocks. It's a young soil. And so those minerals keep breaking down, and at a certain point you get clay. And clay is a colloid, and so the clay in your soil gives it this charge. The other part of your soil's colloid is, of course, the humus. So that organic matter we talked about last week, here's that vanilla soil, by the way, with a pH of 6.6. So that humus is also a colloid. So colloids have this charge on the surface, remember. So the soil, the clay and the humus together in your soil give it a charge. Literally, your soil has this charge on the surface of the colloids. There's other things going on in the soil, there's roots, there's organic matter and all that, but on the specific colloid surface in any soil, there is this charge. And the pH does influence it a little bit, but I'm not going to go there tonight. But suffice to say, the pH does kind of vary the charge sometimes, depending on the pH. And the charge is almost always negative. And the key thing, so the colloid in your soil is the clay content, the type of clay, plus humus, plus the pH. So some soil clays, some clay types don't have a big charge, and other clay types have a big charge just naturally because of the clay colloid type. I won't go into any more than that. Just to suffice to say, different clays do have different charge sizes. So that's what gives your soil its charge, and we measure it in the soil with something called the CEC, which I'm sure some of you will have heard of. It's also known as the cation exchange capacity. So all the cation exchange capacity is it's a measurement of the surface charge on the soil's colloids, which are mostly clay, but they can also be the humus. So that's what we're talking about when we say the CEC. We're just talking about this charge in the soil. Think about it as like a pub. Think about your soil as like a pub, and it's got different rooms in it. And the front bar is like the colloid. So it's really active, and things are exchanging there, like they're on Tinder and they're kind of doing deals or whatever people do on Tinder, I don't know. But just think of the front bar as kind of like the Tinder place where everyone's getting an exchanging. So it's not the only room in the pub. There's the organic matter, there's the VIP lounge, which is your soil solution, where everyone's just burning money really quickly in the pokies, and it's just highly active. But you've got different rooms in the pub, but the really important one is this front bar, which is what we call the soil colloid, or the CEC. So that's what we're going to be talking about for the rest of the night. There's different ways they kind of measure the size of your front bar, and the two main ones is ammonium acetate, and there's one more and more used, particularly in horticulture, but other labs are using it, and that's the Melick 3 method. So they're the two main ways you hear it. And there's different units of measurement, as you'll see on the soil test, C-moles and milliequivalents. Let's have a look at some soil tests. That's probably a better way to do it. So let's get this soil up from Victoria again. Can everyone see? I'm just looking down my list of things on the left-hand side, you know, the usual thing where the lab has laid it all out in a big long list, and you're going, where the hell's what I need to find? And then we'll go down, if I can just work this out, no, just get my screen back to normal. We go down and we have a look towards the bottom. Here it is here. They've measured the CEC, or the cation exchange capacity. They've called it effective, which just means it's been measured at field condition pH. And here's our number, 3.2. So it's quite a small charge, if that makes sense. Does everyone see the really other important thing at this point is that the size of the charge is not necessarily good or bad. It's just my soil type along with texture. If you remember, I've got sandy soil or clay soil. It's not good or bad, they're just different. And it's the same with the charge in your soil, this colloid size, or the front bar, size of your front bar. It's just, I've got small, medium or large. And you'll see that inside this Insight test, the benchmarking, they've said for the benchmark for the CEC is anywhere from 0 to 100. So it's a pretty easy target to hit. So as long as you're between 0 and 100, it's all good according to their benchmark. And you can see that's their way of sort of saying, look, you can have a small or a large one. It's not good or bad. That's their way of doing that with the benchmark. Because at 3, it's quite small, but it's not bad as such. It's just different. And small CCs have advantages and large CCs have advantages, and vice versa, disadvantages. So, yeah, but this one's got a small one. Let's just have a quick look at one more, and then I'm going to get on to the cations. Which one should I pick? Oh, yeah, I'll go to these 9 soils. No, I won't. I'm sorry, everyone. I'll go to this soil. So this is a soil in northern Queensland, a grazing paddock from the EAL lab test. And again, to find it, I've got to hunt down, but here it is at the bottom of the first page. They've put it in here, cation exchange capacity, effective cation exchange capacity. And you can see there it's 7.9, so it's a bit bigger. And they're kind of saying a heavy clay soil is usually around 20. But yeah, again, and you can everyone see that the way they measure, the unit of measurement is C-moles per kilogram. So that's the unit of measurement. And the way it's measured is, in this case, is ammonium acetate, which is actually, it's a calculation, they're saying, but they've actually got it by looking at, if I can scroll up, they're doing the ammonium acetate extraction method. So EAL lays out the method really clearly for you. And it's important because different labs measure it differently. Here's the Horticulture Lab that we've been looking at, Vita, and they have their CEC. They've got it down here. Everyone see that? Here's their CCE, or effective. They use a different unit of measurement, milliequivalents. And there's the result, 10. And you'll notice that they haven't benchmarked it. They haven't said, oh, that's good or bad. They've just left it blank because they know it's a property of soil type. So it's not good, or it's just what you have to deal with. It's part of your soil type. You've got to live with it. Just understand it and manage it appropriately. So you can sort of see they've done there. And in fact, and these guys use the Melick method for extraction, which is at the top of their test. Okay, so you can see there that it's measured as either C-moles or milliequivalents, and most of those labs with both of those units of measurement, they're actually equivalent. So they're equivalent. You can convert them 1 to 1, so it's not too difficult. Sorry everyone. So we found our CECs. If you found yours, feel free to put it into chat there or put it on your worksheet. It's probably better at the moment. It's not good or bad. It just is what it is. It's part of your soil type. You can modify it with pH management and also with some humus. So if you build organic matter, you will increase your CEC to some extent. Not usually hugely, but it can be really important. Just changing it from 5 to 8 or something is a massive change in the buffering capacity, and that humus is helping to stabilize and facilitate equilibrium, if you like, or buffer that soil system, which is going to optimize conditions for life, which kind of makes sense when everything's co-evolving together. Another thing that happens as your soil keeps weathering, so that's the first really important thing to remember when we're talking about cation balances, is that where is this balance happening? It's on the colloid. So I just tried to set the scene by explaining what a colloid is. And the easiest analogy I can give you is like the front bar of the pub. So whatever pub you go to or avoid, just imagine the front bar, and that's where there's quite a lot of lively action. So that's where we're going now. We're going to see who's in the front bar. So another thing that happens as soil minerals weather through time, they create clays and sands and silts, and they keep weathering, they keep breaking down. And at a certain point, at the end of weathering, when you have a little clay mineral and that's almost the end, that keeps breaking down either biologically or just through biophysical weathering. At a certain point, you're left with just nutrient elements. So the nutrient elements get released from the mineral. That's the end of weathering. You can't weather anything further. Once you get your nutrient elements released from the minerals, that's it. Weathering's finished. Time to get a new planet. No, I'm just kidding. Volcanoes will make some new rocks for us. So at that point, the key elements become active in my topsoil. So they've come out of the minerals and they're now kind of pretty lively. So they're no longer in a sleepy state. They've come out and they're pretty lively. So think of when they come out, think of them as coming out into different rooms in the pub or buckets in the soil. So that's the analogy that I'm using here. So I'll just visually do it with this pretty bush diagram, but hopefully it's not too bad. So imagine you've got magnesium here in the mineral, and it's a clay mineral and it's weathering, or bacteria is spitting on it and trying to get some nutrients from it, or natural rainfalls weathering it, or whatever. And at a certain point, the magnesium comes out into the soluble form in the water of the soil solution. So it's in this soil solution bucket. But some of the nutrients, when they come out, they can go and hang out on this charge. Remember that you've got this colloid charge zone in your soil, which has got a negative charge on it. It's almost always negative in soils. So we've got this charge on the surface of these clays and humus, which is our front bar. And some elements, when they come out to play, they go and hang out on that charge. So they go and live on that bucket. So that's what we call exchangeable. That bucket's what we call the exchangeable bucket. And some nutrients bacteria eat them and they go into organic matter, or fungi eats it and it goes into organic matter, or a plant takes it up through the soil solution and then a bit of plant material dies and feeds the organic matter, the nutrient back to the organic matter. All of that stuff's going on. We're just focusing on the colloid, because the key thing about the colloid is it is a really important part of your soil, not the only important part, but it is really important. And the key thing about it is, if I can get this to work, is that when depending on what is hanging out on the colloid, or what is hanging out in the front bar, can influence soil health. So if I get certain things dominating that colloid, it can disrupt my soil function. So what we're looking at now is what's called the soil cation balance. It's sometimes called base saturation. That's just another whole bit of jargon that's used for it. So only some nutrient elements hang out in the front bar. Not everyone goes to the front bar, as you know, if you live in a country town. So when all the elements are living in the house, they're at home in the suburb or around town in their home, they're just in a sleepy state, they're in a dormant state or not very active, that's fine. But when they come out to the front bar, some fans come out to the front bar, or nutrient elements, and it depends on the proportion that's hanging out in the front bar. But there's only certain ones that do it, and it's calcium, magnesium, potassium, sodium, hydrogen, and aluminium. And these guys, there is a few other things, but there's such a small amount that we don't usually worry about them. So these guys are what we call cations. So remember that term before, cation exchange capacity. So these guys are cations, and a cation is just anything, any nutrient or any chemical ion or ion that has a positive charge. So calcium, I think, is 2+, so it's a positive charge. So aluminium's 3+, etc. Potassium, sodium, 1+. So they've all got a positive charge, and the jargon we use for positively charged ions when they're on their own is that they're cations. You'll notice that phosphorus isn't there, sulfur isn't there, boron isn't there, molybdenum's not there. They're not positively charged. They don't live in the front bar. They never go in the front bar. It has got way too many people getting drunk and on Tinder. So there's just no way they're going to go there. So I've just got a chat coming in. Hopefully it's not about Tinder. So no worries, Charlotte. Yeah, so the Haney test, Charlotte's asked there, the Haney test from EAL, it doesn't measure CC, Charlotte. It is a different test, and it's trying to estimate different things in the soil. So it's not trying to measure your colloid size. So that test won't help you with those decisions around your colloid size and what's hanging out on the colloid. It can't help you with that. Its purpose is for to help you get different info. Yeah, so Karen's put in there. Great. So you can see, Karen, you've got varying levels, and I'd suggest to you, Karen, that the soil that has 12 CEC of 12 would have a bit more clay in it probably than the soil that has 4 and the soil that has 6. Without knowing the paddock and without ever seeing you apart from on Zoom, I'd be a pretty confident guess that it probably has a little bit more clay, but it may be that it's full of organic matter. It's in your garden. Okay, so can everyone see we've got these cations that have come out of the minerals, and they've come out of the house and they've gone to the pub, basically. They've left home, they've gone to the pub to watch the footy, good night for that, and now they're hanging out in the front bar. Some nutrients, when they come to the pub from home, they don't go to the front bar, but these guys do, and they're called cations. So we call them exchangeable because although they're sitting on the colloid, they're kind of not, they're static or stable, yet they're quite active. So even though they're sitting on the colloid, they're kind of attached to something, calcium, here we go, sodium, potassium, they can be exchanged by bacteria, can come and grab one off there, or a plant can grab it. A plant root can grab a calcium and take it up. So even though it's kind of like a zone where they're hanging out, it's quite mobile. It's what we call exchangeable because plants can grab some of those nutrient elements from that bucket, and bacteria can grab a nutrient element from that bucket. So it's kind of an active part of your soil for nutrient cycling. It's not the only part of your soil for nutrient cycling, but it's a really important one. But just as importantly, who is hanging in the front bar really can shape soil function. So that's another important thing that we're going to look at now. Okay, so let's keep going. Thanks everyone for your patience. Sorry, I'm on this single screen. So again, I've used footy analogies, and sorry if you're like me, you're a rugby league person because you're from New South Wales or Queensland. But yeah, I'm using AFL analogies. If you don't like sport, I'm trying to think of a non-sport analogy. The best one I can come up with is jelly beans. So just think of jelly beans in a bowl in front of you, and the kids are about to eat them. And that's the same thing here. So we've got a bowl full of colourful jelly beans, or you've got a front bar full of footy fans like here. And so the different footy fans or jelly beans are the cations. And when the jelly beans are in the bag and then you haven't opened the bag, they're kind of like just staying at home. There's no action. They're just dormant. They're in the total fertility, but they're not mucking around. When the footy fans are all at home, they're just kind of watching telly or sleeping or whatever. They're not causing any problem. When they come to the front bar, that's when they're getting exchangeable and people can hook up or go on Tinder or whatever they do. And they can hang out or exchange in the front bar. That's when it's relevant for soils because that's the active part, or not more. It's relevant when they're in the minerals too, don't get me wrong, but this is one of the really active zones in your soil where things happen really quickly and quite strongly. So yeah, that's what we're talking about here. And the question from a soil health point of view is it's the proportion of these guys hanging there that's important. The ratio, that's the critical thing for soil health. So even though nutrients cycle through this bucket, that's good, but just as importantly, or more importantly sometimes, is what is the ratio of these guys, cations, hanging on this CC, because that can influence soil function, like soil structure, or how well soils cycle their nutrients, or if they have toxic conditions. That can actually be influenced by the proportion. So that's what we call the cation balance. So some of you may have heard of that term and you're looking for it. So this is the key thing. So let's look at a few soil tests around this. So let's have a look at it now. So if I go to, I'll start with an easy test, if there's such a thing as an easy soil test in terms of layout. So here is the EAL test. And if we go up to the bottom of the first page, so does everyone sort of see here towards the bottom of this first page on this particular test, this is how they've laid it out. They've got this section here with these different indicators, and you've got calcium and then they've got percentage. Everyone see that? Magnesium percentage, potassium percentage, sodium percentage. You'll notice the other jargon you hear for sodium, that is ESP, which stands for extrasensory perception. Sorry, doesn't it? It stands for exchangeable sodium percentage. And then you've got aluminium and you've got hydrogen. So you can sort of see these are the main cations or positively charged nutrients that when they come out to play in the pub, they'll often hang out in the front bar exchanging on the colloid. They also go to the organic matter room and the VIP lounge, but an important place for these guys to hang out is the front bar or the CEC. And can everyone see that they've measured the proportion the percentage, and that's the soil health aspect of the soil that we want to look at now. It's not so much how much calcium is there as opposed to what proportion of calcium is hanging out in the front bar. So hopefully that makes sense to everyone. Great, I'm glad that I was not too far off the mark, Karen. Okay, so the key thing here is that it's the proportion. And if you have a look at this soil, this first soil, we've got this front bar has 68% calcium hanging in it, 25% magnesium, 4% potassium, a little bit of sodium, and a very little bit of aluminium and hydrogen. And this one has no hydrogen and around the same. This one has a bit more calcium. So you can see they've all got kind of different ratios of those cations on the CEC. Here's our CEC here. So everyone see this soil has a CEC of 2. This is a Northern Territory soil. We've talked about these ones before. So it's got a small charge. The CEC is 2. So it's a small charged soil. But that doesn't matter whether it's small or large. The question is, well, it does matter, but that's the first question. The second question is, what's the ratio of the cations on that charge? So 68% of that small bar is full of calcium fans or raspberry jelly beans, whatever you like to use. And 25% of that jelly bean bowl is full of my orange flavored jelly beans. And 4% is full of the white flavored. Does anyone actually know what white flavored jelly beans are supposed to taste like? Because I never was able to work it out. If anyone can tell me what the white colored jelly beans are supposed to taste like, that'd be good, because I've never worked that out. And then you've got a little bit of these colors down here. So can everyone see that? So we'll come back to that. So just make a note of that calcium, magnesium, and potassium seem to be the main ones hanging out, except here we've got a little bit of aluminium mucking around. So we'll come back to these soils. These are all Northern Territory soils. Okay, so if I just have a look at a few other tests, because different tests, remember, lay things out differently, of course. They all have their own style. So here is our other soil from Victoria, and we've got a cropping field. Here you can see they've laid it out differently, so I have to hunt it out. It's a bit tricky. There's my potassium percentage. Everyone see that? Potassium percentage of CEC. They've laid it out really clearly. 9%, but they've mixed it all up because I want to get the other ones. Well, here's aluminium down here. Aluminium is at 45% of my CEC. Oh, yeah. And they're using this other term, saturation. So what does that mean? It's basically the same thing. And then here's my sodium. Okay, there we go. I'm starting to find them. So there's my sodium percentage cations of CEC. What else we got? Magnesium. There it is there. All right. Can everyone see that? They've kind of put them in there, but it's a bit scattered. Remembering that our CEC is right down the bottom here. So the aluminium, which is really high proportion, it's only a small front bar. So it's a tiny front bar, 3. It's not very big, and it's full of aluminium mucking around, having a party. So can everyone sort of see that ratio is different than the previous tests? Someone's just put something in chat. Jen said that's lemonade. I was kind of thinking it might be, but anyway, I wasn't sure if I was being really stupid. Righto, so the white jelly beans are lemonade. All right, so now we know. So black jelly beans, I suppose, are supposed to be Coca-Cola, I guess. Okay, so let's go back to our theory side of it. So we've got this CEC, or front bar, or bowl of jelly beans, and it's full of different cations. There's 6 main ones hanging in there, different fans. And what I'm saying to you guys is that it's the proportion of the fans, or the ratio, that's important for soil health. Not for nutrient cycling directly, although it does relate to it, but for soil function, it's the balance of these fans. And this is an area of agronomy that's a bit contentious, or it can be a lot contentious, because different agronomists have different theories about what's important when looking at cation balances. So there are some agronomists that focus, for example, on aluminium and acidity. Some of them focus on the calcium-magnesium ratio. So there are different schools of thought. So I'm going to try and take you through it without getting too much people upset. And anyway, they can just comment on it on YouTube later on, and I won't worry about it. But yeah, I'm just trying to give everyone that overview of the different perspectives as we go, and try to find the kind of, I guess, 21st century view on it now, I guess. Okay, so the first thing is that there's three main types of fans that you can have in the pub. The first ones are the non-acid cations or non-acid fans. These are the nutrient cations, calcium, magnesium, potassium, and a little bit of sodium. And they're the ones that you want to have in the front bar, if that makes sense. So if we're watching AFL, generally everyone wants to have, well, they don't want to have Collingwood and Port Adelaide, and they want to have everyone, or they don't mind the other teams unless they don't like Sydney or something like that. So you want to have your preferred fans in the pub, correct? So what you generally want to see on the CEC in your soil is a fair proportion, a majority of the things hanging out there being your nutrient cations. So hopefully that makes sense to everyone. So that soil from the Northern Territory, which we looked at, we have quite a large proportion of our calcium, magnesium, potassium. Altogether, it's making up, well, that's nearly 30. So 30 plus, that's nearly 100% of the front bar has got your nutrient cations. There's hardly any of the non-nutrient cations, which you'd think is really good. So they call that, the old-fashioned term for that, which is still used, is base saturation. How much of your cation colloid charge is saturated with the non-acid things. So the base, I don't think technically they're a base or acting as a base, but they're non-acid cations. So that's what we're looking for. So let's have a look at that soil in Victoria. It has 45% aluminium. So it automatically, we know that it doesn't necessarily have a lot of calcium. And I don't know what's happened to that. Sorry, that page is, no, that's not got it there. Wait, sorry everyone. My streaming is so struggling a bit. Yeah, they haven't given us our calcium percentage on that test, so we can't actually do it. But let's have a look at our horticulture paddock. If you have a look at the horticulture paddock, you can see that calcium, they've estimated the percentage calcium at 48, the potassium at 5.7, the magnesium at 20. So you can see it's got nearly 50% calcium, 20% magnesium, potassium's nearly 6%. So it's got a reasonable proportion of these guys. It doesn't have heaps of calcium compared to the Northern Territory soil, but it's got a reasonable proportion. So you can kind of see that the different soils, depending on their mineral composition, going back to the soil type and the type of minerals that are influencing the soil, you're going to get these kind of ratios, proportions on the colloid. So the second really important thing when talking about cation balancing is what you don't want. So you'll get different agronomists. Some of them will focus on, for example, the ratio of calcium to magnesium, which you can see is one thing you could get off a soil test. Some agronomists don't focus on that at all. They go, oh, that's not very important. I need to just focus on the acid cations. So the acid cations are hydrogen and aluminium. So they're kind of like the least favorite fans. So if you don't like Collingwood and Port Adelaide, then you don't want many of them to be in the bar, or the whole bar will get disrupted. Or if you're in rugby league, then and you're New South Wales, and you might not like the Broncos or whatever. So, you know, they're your least favorite fans. Or if you're jelly beans, then your least favorite colors are the acid cations because they're disruptive. So we don't want too many of them. And the other one that can be quite disruptive when there's too much of it in the front bar is sodium. So we might want a little bit of sodium hanging around. It might be like a Melbourne Storm fan, and we want a couple of them, but we don't want too many of them. So you kind of like, sorry if anyone who's a Melbourne Storm, I personally kind of like the Storm, but I'm just doing the analogy. So we want, if we have too much sodium, it can be disruptive. So the key thing when you're looking at cation balances is we're kind of looking at all of the cations and going, do I have a majority of my preferred cations and not so many of my unpreferred cations? And the other one that can be a problem is magnesium when it's too high. And I was supposed to have put that in there, dispersive cations with sodium, and I do apologise. But when you have excess magnesium fans hanging there, it can also be disruptive to soil structure. So soil structure, sodium can be destructive to soil structure, and so can magnesium when it's quite high. Hydrogen and aluminium are the acid cations, and they can be disruptive because they can negatively influence soil biology, nutrient cycling, and aluminium is toxic. So not only is it like a rat bag, it's like a drunk rat bag. So it's kind of a rat bag that's normally you don't like talking to it, but not only that, it gets drunk and then it's really you don't like talking to it. So it's not only an acid cation, it's a toxic acid cation because it's actually toxic to plants. Most plants can't handle it at all. So you can kind of see we've got this balance that we're trying to achieve. Now, different agronomists have different benchmarks for this, of course. So we want as many non-acid cations, a good proportion, not too many acid cations, and the magnesium and or sodium, we don't want too many of them. Now, the problem is that some soil types naturally have lots of magnesium in them. Some soil types naturally are prone for the sodium to be a factor because of the clay type. So you do get soil types that naturally potentially can be high sodium or relatively high sodium, and others that can be high in magnesium, and that can disrupt structure, especially when you lose organic matter. So in different soil types and climates, you get different proportions, as I've just mentioned. You'll get different proportions in there, and it's the ratio that's important, really, when we're talking about all this. We've found a few ratios, so I'll just keep scooting on. And I'm just going to give you a broad sort of general benchmark. Now, there are some agronomists get very specific and will say things like you need exactly this amount of this and that. I don't personally fall into that school of thought too prescriptively because I have seen soils function really well outside prescriptive benchmarks, and it usually comes down to soil organic matter and biological buffering that's stabilizing that soil, even if the chemistry is not ideal. But yeah, there are different schools of thought on it, so I'm just letting you know that because some agronomists focus on one thing and another, and it will influence what you decide to spend money on. So let's be really clear. How an agronomist or how you read a soil test and which ones you say are important will influence what you actually do. So you could be spending a lot of money and getting a result or not getting a result accordingly. So yeah, I've given you some broad ones, and having said that, you'll see soils that fall outside these ranges that still function well. So let's go through some of this now just briefly to look at a few examples for you. Generally though, you want aluminium to be low because remember it's a rat bag. You don't want too many rat bags in the front bar. You don't want too many black jelly beans or white jelly beans, whichever jelly bean you don't like. It's one of your least preferred guys, so you don't want too much of it hanging around. It's in your soil. Aluminium is in every soil, but it's in the suburb, just sleepy in the minerals, and you don't want too much of it. The reason aluminium gets active comes out to party is it likes acidity. So in some soil types, when they get acid, aluminium comes out as well and parties. So it's like hydrogen's hanging out in the front bar and the aluminium are at home and they get all these text messages saying, oh, come to the bar because there's all these Collingwood supporters here. So all the Port Adelaide supporters get a message saying, let's go and party with the Collingwood supporters. So you kind of get two lots of your least preferred fans in the front bar. So they kind of have a relationship with acidity, aluminium. In some soil types, it's important to note that not all soil types, when they get acid, have aluminium parting as well. So you want to keep it low, generally 5% for horticulture and stuff, but there are some grasses that are a bit tolerant of it. Sugarcane's really tolerant of it. But soil biology is not happy when it's too acidic and there's aluminium. So keeping it low, 0, under 5% is probably a good sort of thing, general recommender. And I know I'm being general. Here's sodium. Sodium, generally you want it under 6%. This is a sodic soil, high sodium at 11%, this picture that you're looking at. And they sowed oats and fertilizers to try and get something to grow because nothing was growing, no pasture was growing. And where they sowed the oats and fertilizer, most of the paddock didn't grow very well at all. You could have fertilized it more, you could have added water to it, it still wouldn't grow because the sodium is disrupting soil function. It's what we call a sodic soil. So you can do whatever you like to it. It's not going to grow better, except in the corner, which is the same rate of oat seed and the same rate of fertilizer. It was DAP at 80 kilos, I think. It's a few years ago now in northern New South Wales, north central New South Wales cropping zone. And in the corner, there was an ant's nest. The same rate of fertilizer, same rate of oats, and ant's nest. So I do have ant power fertilizer for sale at the end of today if you've got sodic soils. But you can just see that the biological dimension to the soil has sort of mitigated or stabilized that sodium, which is normally quite disruptive, especially when you lose the organic matter dimension to the soil. Sodium, when you lose the humus and the buffering and the stability of the biological function, which acts as a kind of stabilizer and self-organizing, it's one of the self-organizing dynamics of a soil, then the soil can lose its balance quite quickly, especially if it has colloid imbalances or colloid risks like high sodium. And you will see soils at 10% sodium that are quite strong, stable, and grow things because they have high organic matter, and the clay is not too bad either. So an example for you. And so we want the good cations, we don't want the acid cations, etc. And I've mentioned that different agronomists have different ratios, and you will see that on different soil reports, but I'm not going to dig into it too far tonight because of time, and it's pretty late at night as well. So I'll just show you a few examples, obviously, quickly. It is a big topic, so I probably won't go too much more. We've had a look at those Northern Territory soils. We've had a look at the Wimmera soil, so in Victoria. So this one's got very high aluminium, which is an acid cation. And if I go up to the pH, so you can see it's 45% aluminium hanging around there in the CEC. So that's acidity. That's part of the acidity. So it must also have a low pH, because remember I said that when a soil has is acid, it means hydrogen is mucking around in the colloid. It means you've got lots of hydrogen because that's the acid cation. So pH is another way of measuring how much hydrogen is in the front bar. There are kind of two ways to do it. Is you measure your exchangeable hydrogen and your pH, and they're kind of coming to the same thing from different angles. But if we go up to the pH on this soil, it has a pH, if anyone remembers, of 4.3 in calcium chloride. So at that low pH, aluminium has come out to party big time. So the pH has dropped. The front bar has got quite a lot of hydrogen fans, so Collingwood fans or whatever you want to, whoever you want to put the boot into. I apologise, Collingwood fans, because I'm not an AFL person, but I just know everyone puts the boot into. And then the aluminium has heard about this acid party and come out to play big time. And aluminium is a toxic element. So obviously here, if we lift the pH up with lime, the aluminium will disappear. The aluminium will all go home to the minerals. It'll literally leave the front bar and go home. Lime is like a bouncer. It's just going to get rid of them. They're going to all disappear. But I have to address the pH or the exchangeable hydrogen to do that. So you can kind of see here it's pretty black and white. If we want to improve this soil, liming is probably going to be one of the things we do. And then I'll show you, let's have a look at the horticulture soil. So here is our veggie paddock. And you can see here they've kind of laid it out a bit differently, but down towards the bottom of the test, they've got base saturation, which is the sum of calcium, magnesium, potassium, sodium, the non-acid cations. So they're saying that your non-acid cations, the good guys, are nearly 75% of what's going on in the front bar. But I have 25% of the front bar has got my acid cations, what they call exchangeable acidity. So that's those hydrogen and or aluminium. And in this particular soil, there's only 5% aluminium. So there's acidity, there's hydrogen, and it's a bit acid, but not much aluminium is parting. So that's a good thing, because aluminium, as I mentioned, is a double rat bag. It's not only an acid cation, it's like an acid cation that's drunk. So yeah, it's really disruptive, it's toxic. So you can kind of see this situation. And if we looked at the pH above, if anyone remembers the pH on this soil, it is in calcium chloride, it is 5.18. So it's acid. It's not super acid, but we were talking about it being marginally acidic. And that's showing in the other way of talking about this marginal acidity is to look down at the exchangeable acidity, because that's really just another way of measuring that, is this thing down here where they're talking about who's hanging out in the front bar, which acid, cations, hydrogen. So can everyone hopefully everyone can see the relationship between those two things. Let's just jump to another couple of examples and then I'll kind of pull it together, because I realize I've covered a lot of ground and I'm probably more confused than you guys sometimes because I'm jumping around like this. But let's have a look at some of those 9 soils that I've been mentioning. Sorry, I'm just zooming it up. So these are just some key properties of 9 soils that we've explored through the webinar series, 9 different soils from across Australia. And if you look at soil number, sorry everyone, I'm just on one computer, so it's hard for me to adjust the screen. So if we have a look at this, for example, soil number, some of these are tropical soils, which always are interesting from an acidity point of view most of the time. So if we have a look at soil number 6, which is a granite soil in the tropics, it's got a pH of 5.2 in water, so it'd be 4.5 pH calcium chloride. It's quite acid. And in this soil, aluminium is 61% in the front bar. So can everyone see that it's really having an acid party? That front bar is just, you don't want to go anywhere near that front bar. And plants won't want to go anywhere near that front bar. And the microbes have had enough, and they've all gone to the ladies' lounge as well. Everyone's left the front bar except the super rat bags. And you can see there's also hydrogen in there as well. So that's nearly 80% acid cations. This one here is a pH of 4.6. It's even more acid, but it doesn't have as much aluminium, only 20% only. It's still very acidic, and it's got more hydrogen. It's still acid, but not as much aluminium in the front bar, so plenty of hydrogen mucking around. And you can see the soils that are near 7, so 6 and above, or even over 5.8 sort of thing. This first soil, which is a heavy clay, volcanic derived clay in southeast Queensland, near 7, there's no aluminium and no hydrogen. There can't be, because they're the acid cations and it's nearly neutral. So can everyone see that it's just another way of measuring it? But you can't measure aluminium with the pH, so that's why it's good to get exchangeable aluminium if you suspect it's a problem. But when you're over around a pH of 6 or thereabouts, it depends on the soil, you're not going to have aluminium mucking around because the hydrogen's not there much. And over here, this is the vanilla soil in the tropics that they haven't lined. All they did was mulch and build humus. And you can see that its pH for a tropical soil where acidity is a problem has stabilized because of that buffering and biological self-organization, if I can use that term, if everyone's not too as happy with that term. So you can see it's chemically quite stable, and in fact the cation balances are very good no matter which school of cation balancing theory you take. You'd be happy with that generally. So, and that's all really just through, I guess, biological self-organization of humus formation in what I'd call a forest soil. So yeah, you can kind of see what's going on there, and that's kind of an extra dimension, I guess, to 20th century soils, where not only does the colloid chemistry like acidity and aluminium and sodium influence your plants and life, but it's vice versa. Those things also modify the chemistry. It's a two-way relationship. So I guess that's the point I'd really like to leave with you tonight. So you can use plants and organic matter to help modify chemistry, but you can also use chemistry to help modify the conditions for plant growth. And there are times for both of those tactics, I guess. So I'll kind of leave it there. Yes, liming, gypsum, dolomite, those minerals are usually part of the mix when we're talking about this, but there's often other things like humus building is such an important aspect. And the cation balances, hopefully you can see that as your humus and biological function and status improve, they become less of an issue. I'm not saying that they're not an issue, but they do definitely become more moderated by really good organic matter and biological function. And today we were looking at a high magnesium soil, one of the case study farmers, the farmers had in their case study they brought along. And it's got very poor structure. It's heavy clay with high magnesium. It sets hard, it shrinks, swells, very problematic. It's lost its carbon and organic matter through farming history. It's kind of lost its mojo. And so the magnesium is now really dominating and causing problems. So yes, you can fix it, I guess, with gypsum, which kind of adds more calcium and therefore moderates the magnesium, but it's not a long-term fix. You've also got to get organic matter and roots and biologically created structure back in that soil, because the organic matter created structure can help overcome that high magnesium property of the clay type. So hopefully that makes sense. I've kind of scooted through a little bit. There is a bit more to that cation balancing we could investigate, but I'll pull it up because of time. I'll just make sure I'm so again, if you feel you've got a soil constraint after looking at that, please do it. And we've talked about the different minerals. It's not black and my opinion, it's not black and white though. Sometimes agronomists will make the cation balancing very black and white. Some agronomists make carbon very black and white. We've got to look at field conditions and all the other aspects of my soil before making that diagnosis, I guess. So on that note, humus is one way you can build it up, and that's just a photo of humus. Yeah, I'll have a look at any last questions in the chat and then I'll pull it up. But basically, yeah, we've covered a fair bit of ground. And at the end of session 3 now, I've got you through the cation balances and pH. And so really salinity is the next one, which I should have taken that off there. I apologise. That's what we will be covering off next time. So I'll just doing that. And next time it's about soil salinity. And I'll just introduce you to some of the things you can do to check your soil health in the paddock, because that's really important too. Okay, so I'll just have a look at the chats and then I'll pull it up, Catherine. So we'll see what questions that I've missed have come in. Wow, I've missed heaps of questions. Sorry, everyone. Oh no, not too bad. The white jelly beans is lemonade. So sodium is 24%. Okay, so Jen, that's technically a highly sodic soil. So if it's been farmed or disturbed and has lost its vegetation, particularly grasses and sort of stuff that would keep it stable, then the chances of it eroding, sealing on the surface, eroding away if there's creeks nearby, are very high. So sodic soils, they have very little structural integrity when they lose their organic matter. So they're very problematic, and it's very hard for a lot of plants to grow as well. So yeah, that's highly sodic basically. Just sell the farm. No, I'm just kidding, Jen. There are things you can do, but it depends on the context. Charlotte, no worries. Charlotte, it's probably better if you contact me, just because I'm on the road. So if you wouldn't mind, I think, okay, I'll just get your email and I'll send you through, but probably better if you can email or ring me, Charlotte, about that, just following up on that theme for the school there. That'd be fine. Dispersive soil is likely. No, it means that that means it'll fall apart, Jen. Dispersive means it'll fall apart. The clay will just come out and it won't have any structure and you won't grow things well. There'll be no air getting in. Then it'll set hard when it's dry and seal on the surface. So yeah, Charlie, if you can contact me, that'd be good. Okay, cool. So yeah, I think that's it. I think I've covered it there. Oh, there's one more new message. No worries. Yeah, I think I've got them all there, Catherine. So yeah, I'll pull it up, everyone. Thank you for coming in once again to the little webinar series that we're running, and I hope you got some food for thought and you're starting to sort of get a feel for the process of assessing your soil with a soil test. But also it is really important to learn how to assess your soil in the field with a spade and looking at structure, etc. And I'll see you guys next week when we'll tackle soil salinity, field assessment of soils, and kind of pull it all together, I guess. All right. Thanks, Catherine.
Great. Thanks very much, David. And thank you, everyone, for joining us tonight. Between sessions, if you do have any questions that pop up during the week, please feel free to send me an email and we can collate them and send them through to David to touch on at the start of next week. Again, thank you very much to Wimmera CMA and the funding from the Australian National Landcare Program for making this free to everyone. Thank you very much for joining us, and we'll see you next Wednesday at 7:30 for number 4 in the series, the final one, David.
No worries. Thanks, everyone. Yeah, no, I hope you're getting some food for thought from it. And yeah, I'll see you next week, Catherine and everyone.
Great. Thanks very much, everyone. Good night.
Take care.